Hey guys, what's up? Happy Valentine's Day. I thought I'd do something fun for Valentine's Day, and today we have a cardioid. And I'm plotting this cardioid 2 plus 2 cosine theta from 0 to pi. So the classical thing to do would be to find the area of such a region. But what I'm going to do today instead is actually take that region and I'm going to rotate that about the x-axis. So I want to find the surface area of the solid obtained by rotating this polar curve about the x-axis. So basically this surface here, I'm going to find the surface area of that surface. And to do that, we're going to just use the classical surface area formula. Area equals integral from a to b 2 pi y times the square root of 1 plus dy dx squared times dx. So that's really, if you've seen it in the book, sometimes it's written as 2 pi y ds. So that's square root term times dx. That's often called ds, differential arc length. Well, differential arc length, it can be written as square root of dx squared plus dy squared. Notice in our polar equation, r equals 2 plus 2 cosine theta, I don't have x or y anywhere in there. That is an equation in polar coordinates. So what I need to do is convert my ds into polar coordinates. So I'm going to do that by switching x and y into polar coordinates. Then I can see that dx is r prime theta cosine theta d theta minus r sine theta d theta. That's just by taking the product rule and treating r like a function of theta. And same for dy, just treat r like a function of theta. So you do the product rule, r prime of theta sine theta d theta plus r cosine theta d theta. Square those. Obviously, I'm just going to factor out the d theta and then square those terms. Then I'm just going to add them together. So dx squared plus dy squared will just give me r squared plus r prime squared. And then I can factor out the d theta squared and just take d theta out of the radical entirely. So ds in polar coordinates is just the square root of r squared plus r prime squared when you square those out. And we use some trig identities. So that's going to be how we change everything into polar coordinates. So y, of course, is r sine theta. And then our radical becomes the radical of r squared plus dr d theta squared d theta. And we just plug in what r is in terms of theta, which is 2 plus 2 cosine of theta. And then take the derivative dr d theta, that's negative 2 sine theta. So square that out, so we're going to get integral from 0 to pi, 2 pi times 2 plus 2 cosine theta sine theta, square root of 8 plus 8 cosine theta. Again, a lot of trig identities are just going to happen under that radical to simplify everything down. And then to integrate that, I'm just going to do a w substitution. W equals 2 plus 2 cosine theta. And dw then, of course, is negative 2 sine theta d theta. Change the bounds. 0 becomes 4. Pi becomes 0. Then we have integral from 4 to 0, technically. And then we have a negative out front. W square root of 4w dw. Shucks. So that integral is going to be 128 pi over 5. Happy Valentine's Day.